Welcome to the last video with the binomial theorem. If you go to the back page of this binomial power notes sheet, you'll see the binomial theorem written down. Now, I do want to point out it looks a little weird, but this is another way to write this, and this is another way to write that. Because remember, these coefficient numbers, the numbers that are in the front that we're multiplying by, come from either Pascal's triangle or you doing this combination feature on your calculator, right? So this whole thing is the same thing as n combinations choosing 2, and so on and so forth. Now, if you notice, this is doing exactly what we did. We started with the first term, and we're taking it to the nth power. And then we're taking it to the n minus 1, drop down 1. And then n minus 2 drops down another 1. All the way until the a disappears. And then we're starting with the second term to the nth power. Okay, second term to the nth power. And then go back and drop 1 power, and it goes all the way down until the b disappears. So this is one way of saying the binomial theorem, but I think it's a lot easier to see if you think of it as 3 things. And so I want to jump to number 8 here. Think of it as 3 things. The first thing is I need to know which row on Pascal's triangle, or what's the total number, the n value in my NCR. This number, the exponent, is the n. And then we can figure out the values either on the calculator or by using Pascal's triangle. But if I use Pascal's triangle for row 3 here, row 3 says my numbers, my values are 1, 3, 3, and 1. Great, I'm done with that part. The second part, take a look at the first term and take it to that power. But notice this time I have a 3 and an x. So then the first term will include 3x to the third power. The second term is going to have 3x to the second power, 3x to the first power, and then this would be 3x to the 0 power, but that means there's no 3x. Okay? So now we go back, and we're going to do the second term to that power, but we're going to start at the end. So we're going to multiply by 7 to the third, 7 to the second, 7 to the first, and then this would be 7 to the 0, but I'm not going to write it because that means there's no 7. Let's put the plus signs in between, and we have our answer. Now, is it simplified? Well, no, it's not really simplified. And that's what we're going to do on Monday. We'll come back and we'll clean this up. But this is the pattern that the binomial theorem at the top is telling me I can do. That if I know what the coefficients are, I take the first term to the original power, and then I drop the power down 1 exponent power every time. I take the second term to the original power, start at the end, and go backwards and drop it 1 every time. I'm going to try to fix these exponents that look all scribbly here. So this should be 1, this should be squared, and this should be third, and this should be a 7. Even though it doesn't quite look like 1, it should be a 7. This draggy pen is not helpful. Okay. Our goal on Monday is going to be to clean this up. But you've set up the blueprint. This is it. This is the answer. And we're done. If you go to number 7, we can do one of those. Or we can do something like number 9. So, when I'm going to do number 7 and number 9, just to let you know. This is the last video, so this is the last thing you'll fill in. For number 7, I start the same way, which is I'm going to go to the 4th row of my Pascal's triangle, or I'm going to use my NCR, where n is equal to 4, and I'm going to write out those terms. So if I go to the 4th row of the triangle, I believe these are the numbers that you see. Great. Now, I'm going to go to the first term and take it to the original power, to the 4th power, and that's what I write first, x to the 4th. And then the next one, x to the third. And then the next one, x to the second. And then the next one, x to the first. And then the last one, no x, x to the 0. Okay, take the second term. But when I look at the second term, I got to be careful. There's a minus there, so I got to include it when I write it. So this is going to be negative 5 to the fourth, negative 5 to the third, negative 5 to the second, negative, I'm having a little bit of trouble with my pen here, negative 5 to the first, and then this one has no negative 5. It's negative 5 to the 0. Now, did I do these right? Well, remember, if I add the exponents 2 and 2, I should get 4. This x is to the first power, so 1 and 3 together, that gives me 4. 3, and this should be 1 right here, so 1 and 3, that gives me 4. Okay, so I'm on the right spot. I'm in the right area here. So put plus signs in between, and on Monday, we're going to simplify this to make it look a little bit nicer. And also, hopefully, I will have fixed my pen by that time as well. And we're done. This is the binomial theorem. What is the binomial theorem? It's a pattern that allows us to multiply binomials efficiently so that I don't have to multiply them actually using algebra. It's a shortcut. That's what the binomial theorem is. But it uses numbers, like the ones in yellow here, that come from either Pascal's triangle or the combinations that we did on our calculator. But I want to jump to let's do number 10. Number 10 says, we don't want to expand it. We just want the x fourth term. So I want the term that's going to have x to the fourth in it. Okay. Well, in order to have x to the fourth, that means this has to be to the fourth because that's where the x is. And if I take it to the fourth, that'll be x to the fourth. Now, it's also going to be 3x to the fourth. So eventually, I'll have to do 3 to the fourth power, but x to the fourth because that's what I want. And then the second part, remember what we said? The exponent here has to add to the other exponent to give me the original power that I started with. So 4 and 1, that gives me 5. That's how I know what this is. But now I need to figure out the value that goes here. And for me, the quickest way to do that is using my calculator. And if I do 5, let me change the color here. If I do 5 combinations where you're choosing 4, that's going to give you the number that goes there. Or the other way to think about it is 5, because that's the original power, combinations of 4, because this is the power of x. By the way, if I plug a 1 in here, I should also get the same answer. 5 choose 4 is going to give me 5. Oh, let me use the yellow color here. This is not simplified, but this gets us to where we want to go today. How do I know that this was it? Oh, because I wanted x to have a fourth power. Well, out of the two terms, this is the one that has the x, so let me take it to the fourth power. But if this goes to the fourth power, that means the second term has to go to the first, because if you add 4 and 1, that gives you 5. And then to figure out the number that goes in the front, the Pascal's triangle number, I did that 5 choose 4, and I put it in there. Okay, let's try it again. And we're almost at the end here. I want the x to the 8th term. So think about it. Out of this term or this term, which is the one that has the x? Well, the first term does. So I'm going to take the first term to the 8th power. Why? Because that's the one I want. But if that's true, what's left is negative 4 to the something power. How do I know what this is? Well, because this exponent and 8 have to add up to 12, so this has to be 4. And then to figure out the number that I multiply in front, I'm going to do 12 combinations where you choose 8. 12 because that's the total number, 8 because that's the one that I want, and this is going to give me the answer that I need. 12 choose. Twelve combinations where I choose 8. Let's see what that equals. Oh, I guess I can use my handy-dandy calculator. Silly Mr. Barrientos. Or maybe I can't. Well, 12 combinations where you choose 8 is 495. That's a ginormous number, but that's what the answer is, and we have finished. So the moral of the story for this week was the binomial theorem is a way to use patterns to find a shortcut to multiplying things out. That's our goal, to make something complicated less complicated.